Hello everyone, today in this video we'll be discussing about the third module of physics, which is quantum computing. Okay, so in this module we have the matrix and its operations. It's a very easy module. You just have to know the different kinds of matrices. If you watch this video till the end, you'll be able to score more than 80% marks in the exam. So make sure you watch till the end, and make sure you hit the like button, subscribe to my channel for more videos like this. Without wasting more time, let's get started. So the first topic is principles of quantum computing. Okay, so let's first understand what is quantum computing. Okay, so like normally we use the bits and zeros and ones, right? Like that we have in quantum computing terms as this one, qubits. Okay, so what happens is these two has some special properties, okay, which we'll be discussing. So that is called as quantum computing. So here it can exist both as 0 and 1 at the same time. Okay, and it is exponentially faster. And in the classical bits we have either 1 or 0, right? 1 or 0, and these are represented in the transistors and the circuits, but in the qubits we'll be representing them by using the electrons, protons, and neutrons, and very small subatomic particles. By using them we will be representing. Okay, and it's much more faster. So the quantum bits are called qubits, and the computers that use such bits are called quantum computers. Okay, and this is the spin of an electron, downspin, and this is the upspin. So this is represented as 0, and this is represented as 1 in qubits. Okay, so qubits use electron, protons, and neutrons for storing the data. Okay, so why we need the quantum computing? Okay, for that we need to understand what is the Moore's law and its end. Okay, so Moore's law states that the number of transistors in an integrated circuit doubles about every 2 years. Okay, means when we make the transistors and the circuits, at that time the number of transistors increases two times every 2 years. Okay, so that is an observed pattern from the previous many years. Okay, so it assumes that it will happen indefinitely, means forever it will happen, but that's not the case. It will end. Okay, and it's the end is very near. Why it is going to end? Because the circuits cannot be made more smaller. It has reached 3 to 4 nanometers. Okay, 3 to 4 nanometers it has reached, and more smaller if we do, we cannot maintain it. Okay, and it will not start functioning. It will start interfering with the quantum computing. Okay, so that's why we need some other method for storing the data and computation, which is called as quantum computing. Okay, that is happening at a very very smaller level, less than 3 to 4 nanometers. Okay, where the classical bits cannot reach, the quantum computer computing is going on there. Okay, so let's understand what is the difference between classical and quantum bit. Okay, so classical bit will be either 0 or 1. Okay, 0 means low and 1 means high. These two are the only possible states, but a qubit will have an interposition, superposition of both of these. Okay, it will be having a 0 here and a 1 here, and any value in between them, and they can exist as a superimposed state between 0 and 1. So 0 plus 1 divided by root 2, like this kind of state is possible. Okay, due to this kind of state only the faster calculations can happen. Okay, so it has few of its properties. The first property is it can be represented as a downspin or an upspin, which is equivalent to 0 and 1, and it can be in a superposed state of 0 and 1 both together, which will be represented as the wave function alpha into 0 plus beta into 1. Okay, where alpha and beta are the complex numbers whose squares sum is equal to 1. Okay, and an important thing is that we cannot copy paste a qubit as we do like the bits. Like for example, if there is a text here AB, okay, this is equivalent of some classical bits. We can copy paste it and it will still remain AB. But in the quantum computing, the qubits cannot be copy pasted because it will be a different qubit when we paste it. Okay, that is called as no cloning theorem. And two qubits are interrelated. Change the one state and it will be affected in the other state. Means change the value of A, the B will be affected. If this is 0, this is 1, and these both are superimposed, change the value of A here and the B will also be affected. Okay, no matter how much far they are from each other, and this feature is called as entanglement. Okay, so how do we represent the qubits? The qubits are represented by a Bloch sphere. It's a very important question from exam point of view. As you can see here, this is a 3D sphere here. So here we have the x-axis, here we have the y-axis, and here we have the z-axis. Okay, and the top is the 0 here. This north pole is 0, and the south pole is given as 1 here. So the angle between the z-axis and the green line, that is theta, and the angle between the x-axis and the shadow of green line, that is the symbol here. Okay, so two angles we are considering here, and the green line is nothing but the wave function at that point, like superimposed state of 0 and 1, that at this point, that is given by the wave function here. Okay, so a Bloch sphere's equation is given as cos theta by 2 0 plus e I power and this symbol into sine theta by 2 into 1. Okay, moving on to the next topic, which is single and two qubit and extension to n qubits. Okay, what is single qubit? Single qubit can be either 0 or 1. Okay, so it can be represented as like this in the matrix form 1 0, and the 1 will be represented as 0 1. Okay, the matrix for single qubit is this. Okay, so when we combine, first we write 0 here, then we write 1 here, so it will become as 1 0 0 1. This is the matrix for the single qubit, 0 and 1 both. Okay, so pictorial representation for alpha 0 and beta 1 is this one. Okay, this is the 1 qubit. Similarly, 2 qubit has 4 states. Okay, 0 0 1 0 0 1 and 1 1. So the matrix will be also as follows. In the diagonal only 1 will be there, rest all elements will be 0. The pictorial representation is like this, 2 qubits. Okay, so in the same way we can extend it to n qubits, and the pictorial representation will be as follows. Moving on to the second topic, which is Dirac representation and matrix operations. Okay, so the wave function could be represented as the KET notation, ket notation, which is given as this one. So this is called as the ket notation, and this symbol is the wave function. Okay, ket notation is nothing but the wave function's representation. Okay, so ket notation is equal to alpha 1 alpha 2. This matrix is given here, so the states will be 0. If it is 0, it will be 1 0. If it is 1, means it will be 0 and 1. Okay, so alpha 1's value and alpha 2's value is dependent on if it is 0 or 1. It will change accordingly. Okay, so what are the few operators we have in the quantum computing? The first is the identity operator. It is similar to multiplying by 1. Okay, 1 is the identity operator in multiplication. Similarly, we have the identity operator I, which is given as circle bracket here, and 1 0 0 1. Okay, it is called the identity operator. Why it is called the identity operator? It's because when we multiply 0 and 1 states with this value, we'll again obtain 0 and 1 only. Okay, see, here we will multiply 0 with I. Okay, so what we obtain, I value here and 0 value here. So when we do the matrix multiplication, what happens? 1 into 1 plus 0 into 0, that is equal to 1, and 0 into 1 plus 1 into 0, that is 0 plus 0, that is equal to 0. In the same way we will obtain for 1 as well. Okay, so the operation of the identity matrix does not change the state, it remains the leaves the state unchanged, 0 to 0 and 1 to 1. Okay, next we have the Police matrices and their operations. Okay, so there are four Police matrices which are very useful. So the first one is the identity matrix, second is the X matrix, Y matrix, and Z matrix. These three are known as poly matrices. Okay, so what is the X matrix? 0 1 1 0, just the reverse of this one. Okay, here we have 1 1 0 0, here we have 0 0 then 1 1. Okay, and Y matrix is 0 0, 1 is same here, but here it will be minus I, and this one is similar to the first one, identity matrix, except that the last one will be minus 1 here. Okay, so these four matrix will be doing the operation on 0 and 1. Okay, so let's have a look how it goes. So for the 0 for the identity operator and 1 for the identity operator, the result remains same. For the X operator, this is the result. 0 will become 1 and 1 will become 0. It will reverse it. Okay, so the X operator is reverse. Okay, X operator is reverse. And then we have the Y operator. Y is 0 and 1 here. When we apply the Y operator, we'll get I1 here and minus I0 here. Okay, and for the Z operator, what we have here, we will be getting as 0 for 0, and for 1 we will be getting minus 1. Okay, instead of 1 we will be getting minus 1 here. That is the Police matrices. Moving on, we have a very important matrix, which is the conjugate of a matrix. Okay, so in conjugate of a matrix, what happens is, so in conjugate of a matrix, if we have A as I 1 0 2 minus 3I. Okay, so conjugate will be given as here it will become minus, and here it will become 2 plus 3i. Okay, so this is called as the conjugate of a matrix. And next we have the transpose of a matrix. Transpose means we have to interchange the rows into the columns. Okay, like for example, if a is given as this here, so the transpose of a matrix will be I0 will come in the row here, and this will be come in the this part here. So the column became the rows, right? So this is the first column, here it is the first row, this is the second column, this is the second row here. So AT is the transpose of A. So if we perform both together, conjugate transpose of a matrix, then we obtain as follows: I 1 0 and 2 minus 3i. So when we do the conjugate and do the transpose of a matrix, we'll be obtaining minus I1 0 2 plus 3i. So A plus is the conjugate transpose of A. Okay. Next we have the Hermitian. So the matrix that is equal to its conjugate transpose is called a Hermitian. So suppose that there is a matrix here, and we do the conjugate matrix conjugate transpose, and we obtain one matrix. If these both are equal, at that time it is called as Hermitian. Okay. So for example, when we do the complex conjugate and transpose of the matrix, what we obtain is the same matrix which is present here. Okay. So that shows us that A plus is equal to A. Okay. So A is this is the A star. So what will be A? A will be equivalent to this one here. Okay. Just have to change the plus here, and this will be minus here. So this was A initially, and the transpose of A star will be this one, which is equivalent to A. Okay, so A plus is equal to A, that is equal to that means it's a Hermitian matrix. Next we have the unitary matrix. Unitary matrix means, so u plus into u should be equal to I. Okay, if that happens, then it is a unitary matrix. Take any matrix here, find out the conjugate of it, and then find out the transpose of the conjugate, and then multiply this value with the u. Okay, so when we do that, we'll be obtaining one one matrix will be obtaining, and if that matrix is in the form 1001, then it is called as the unitary matrix. Okay, so u plus, if you multiply, I should be obtained. Okay, so whichever matrix satisfies this condition, that is called as unitary matrix. Next we have the row and column matrices. Okay, so the column vectors are represented by this symbol, wave function, and are called as ket vectors, and the row vectors are represented by this symbol and are called as bra vectors. Okay, so here we have the ket vector alpha 1 beta 1, and here we have the bra vector. So just the symbol changed here. Okay, so this is the row and this is the column matrix. Okay, and here will be representing as star, and here also will be representing as star, and these both are equivalent. If we find out the conjugate transpose of this, that will be equivalent to the bra vector of that. Okay, so the bra and the is the complex conjugate of ket and vice versa. For example, 1 and I here, find out the conjugate transpose of this one, 1 I plus is equal to I into minus I 1 into minus I, 1 and minus I. Okay, this is the row and this is the column. So flipping between ket and brass is called as taking the dual. Okay, so for 0 and 1, similarly we have for 0 will be representing as this one. If we take the bra vector of it, we'll be obtaining the row matrix as follows. Okay, so for the 1 also we have the same thing. 0 1 will be here. If we take the bra vector, we'll be obtaining this one here, 0 and 1. Next we have the inner product, which is also known as the multiplication of the rows and column matrix. Okay, so if you multiply both the row and the column together, it is called as inner product. Okay, very important question from exam point of view. So let's consider the two states, this state and this state. So this state is represented by alpha 1 beta 1, and this state is represented by alpha 2 and beta 2. If we take the bra vector of this one, so we'll be obtaining here alpha 1 star and beta 1 star. So we'll be multiplying this one with this one. Okay, these two will be multiplying. Okay, so when we do the multiplication of these two, we will be obtaining the following here, and when we expand it, we'll be getting alpha star a, alpha star, alpha 1 star alpha 2 plus beta 1 star beta 2. Okay, so the inner product will always result in a scalar product. Okay, this is a very important observation. Next we have the probability. So let's consider a quantum state. So here we have alpha 0 plus beta 1, the wave function is given. The above equation represents the quantum superposition of the states 0 and 1. So if this kind of equation is given, it is a superposition. Okay, and if we expand what is 0 and 1, we'll be obtaining alpha into 1 0 plus beta into 0 1, because 0 is equivalent to this and 1 is equivalent to this. When we do the multiplication here, we'll be getting alpha and beta. So the inner product of this is given by alpha star beta, beta star into alpha and beta. So that will be alpha alpha star plus beta beta star. Okay, so alpha alpha star plus beta beta star is nothing but alpha square plus beta square. Okay, so this can also be written as the square is equivalent to the wave function into wave function star. So this above equation is representing the probability density. So as per the normalization, the wave function star is equal to wave function into wave function star, and that is equal to the inner product, and that equivalent is 1. Why it is 1? Because alpha square plus beta square is equal to 1 in conjugate complex theory, and that is equal to alpha square plus beta square. This implies the function wave function is normalized. Okay, so this function is normalized because it's equivalent to 1. Okay, so these are the few things which you need to write if they ask about the probability density. Next we have orthogonality. Okay, so what is orthogonality? If we have two states, this and this, they are said to be orthogonal if their inner product is 0. We will be multiplying these both inner product, calculating if it is equal to 0. That means it is orthogonal. Okay, so why it is coming as 0? It will come as 0 if both are separate by 90 degree. Okay, like for example, if it is spin up and spin down, then the multiplication will be 0. Okay, so consider 0 and 1's multiplication, both are opposites, right? So it should be 0. So 0 and 1, when we multiply, first we'll write for 0 and we'll write for 1 here, and when we do the inner product for the row into column, we'll be obtaining 0 plus 0, that will be equal to 0. Even if we do for 1 0, we'll be obtaining the same answer, which is 0. Thus the states 1 and 0 are orthogonal. Okay, next we have the orthonormality. If there are two states and they are said to be orthonormal if these both are normalized, that means the inner product of this and this both are equal to 1. Okay, and this are orthogonal to each other, so the inner product of these both should be equal to 0. Okay, let's move on to the third and the last topic, which is the quantum gates. So here we have the two types of gates, like how we have the logic gates like not and nor, and also we have the control gates. Like that, here also we'll be using the quantum gates. Okay, so slightly different thing will be there, but the analogy is 90% similar. Okay, so we have single qubit and we have multiple qubits. Let's have a look at the single qubit. So quantum gates are nothing but logic gates like not and or, etc. Okay, the first one is the single qubit. Here there are 5 types of gates in single qubit. Okay, first is not gate, second is poly gates, and this is Hadamard gate, and this is phase gate, and this is T gate. Okay, so these both are similar to each other, and this we already know both of them from the previous topic, and this is one new thing which you have to know, and this is very very important from exam point of view. Okay, so let's have a look at the first one, which is not gate. Not gate means negating, means making it reverse. Okay, so not gate converts 0 to 1 and 1 to 0. Okay, so how does the matrix representation of quantum gate look like? So this is the matrix representation 0 1 1 0. Okay, this is the not gate. If you want to convert 0 to 1, we have to multiply 0 with this matrix. Okay, this matrix you have to multiply 0. So if you want to convert the 0 to 1, we are multiplying x with this one. Okay, so x is this one and 0 is this one. When we multiply, we'll be getting 1 here. Similarly, if you multiply with 1, you'll be obtaining 0 here. Okay, so quantum not gate on the quantum state is given by, so alpha and beta here, 2x. If you multiply them both, it will become beta and alpha. Okay, it will just reverse it. So the two table you have to make here, the input and the output. So input is first 0, then 1. Then we have the function here, superimposed state function. So here we have for 0 it will become 1, for 1 it will become 0. For alpha 0 and beta 1 it will become beta 0 and alpha 1. Okay. Here also the same thing, the same which you have written here, just write here and make a box and write x here for representing the NOT gate. And here we have the output result, which is beta 0 plus alpha 1. Moving on, we have the second type of gate, which is the poly X and X, Y, and Z gates. Okay, so X gate is nothing but the quantum NOT gate, similar to the same as one which we have discussed previously, and Y gate is represented as the sigma Y or capital Y. So what it does, it will convert 0 to I1 and 1 to minus I0. Okay, this is the change which happens in the Y matrix. Okay, so the Y matrix is represented as 0i and minus I0. Okay, so if you multiply this with 0, we have to obtain I1, and if you multiply this with 1, we will be obtaining minus I0. Okay, so if we write the alpha and the beta equation, so it will become y into alpha 0 plus beta 1, that is nothing but y into alpha and beta, so it will become minus I beta 0 plus I alpha 1. Okay, and we have the quantum y gate representation. The input you have to write here, the same input, and the output which you get minus I beta 0 plus I alpha 1, and in between we have to write y here. Okay, and the truth table is also similar. 0 will become I1 and 1 will become minus I0, and alpha 0 plus beta 1 will become minus beta 0 plus alpha 1, I alpha 1. Okay, the third gate is the which we have in the polymatrix is the Z gate. So it is represented as sigma Z or Z. Okay, so it maps k to minus 1 power k into k. Okay, so if it is an odd number, it will be minus, and if it is an even number, it will be positive. So here we have the 0 which remains unchanged, because minus 1 power 0 will be equal to 1, and here k will be 0. Okay, so 0 will be 0 only, but 1 will become minus 1. How it will become minus 1? So k's value will be 1 here, so it will become minus 1, and since k is 1 here, it will be minus 1 into 1, so this is minus 1 1. Okay, and the matrix presentation and the operation of the Z gate on 0 and 1. So if we do the operation of means the multiplication of Z gate with 0 and 1, what we obtain is, if you multiply Z with 0, this is the Z, and if you multiply with 0, we'll be obtaining 0 itself, and if you multiply it with 1, we'll be obtaining minus 1 here, and if you multiply the alpha 0 and beta 1 here, we'll be getting Z alpha and beta here, alpha 0 and alpha will remain same, beta since it's associated with 1, it will become minus beta here. Okay, and the circuit symbol and the truth table is given here. This is also similar to the equation given here, and here it's a summarized form of these three equations here. That's the truth table. Okay, moving on to the Hadamard gate, it's a very important gate. It's called as self-inverse gate, and it's a very one of the most used and important gates in the quantum computing. So the matrix representation of Hadamard gate is 1 by root 2, very simple, and we have to fill all with ones except the last one. Okay, 1 by root 2, fill all with ones except the last one. Okay, so Hadamard gate satisfies h plus into h is equal to 1, which means it is a unitary condition. Okay, so what does Hadamard gate signify? Why it is so important? It's very important because it gives us the equation for superimposed state. Okay, so for 0, Hadamard gate can be written as 1 by root 2 0 plus 1 by root 2 1, and for 1 it will be given as 1 by root 2 0 minus 1 by root 2 1. Okay, so for 0 it is this one here, and for and the condensed form is this one, and for 1 it is this one, the condensed form is this, and for alpha 0 plus beta 1, here we'll be multiplying the Hadamard value with the alpha and beta, so we'll be obtaining this equation, alpha plus beta and alpha minus beta. Separating them, we'll be obtaining these two terms, for alpha with 0 plus 1 by root 2, beta with 0 minus 1 by root 2. Okay, the fourth gate, we have the phase gate or the S gate. What it does is it turns the vector 90 degrees, 90 radians around the Z axis. Okay, what does S gate do? It turns the vector 90 radians in the Z axis, around the Z axis. So S plus S is equal to I, which means it's unitary, and it turns 0 into 0 and 1 into I1. Okay, so matrix representation is given as follows: S is equal to 1 0 and 0 I. So I can also be written as e power I by I pi by 2. Okay, so the effect of S gate on the input 0, if you multiply the S gate with 0, what will happen is, this is S gate and this is 0. When you multiply, we'll be getting 0 only, but if you multiply with 1, we'll be obtaining I1 here. Okay, and if we write in the equation of alpha 0 plus beta 1, we'll be obtaining S into alpha and beta, alpha 0 plus I beta 1. Since B is associated with 1, we'll be getting an I here. Okay, and the truth table and the circuit diagram is also similar to the one which is given here, alpha 0 plus beta 1, and it's passing through the S, and we'll be obtaining alpha 0 plus I beta 1. Okay, and the truth table is the condensed form of the equations which are given here. 0 will be remaining 0 and 1 will be remaining 1 will be turning to I1, the since it's associated with 1, I will be coming here, and alpha 0 plus beta 1, alpha 0 plus I beta 1. Okay, So the last one we have is the T table or the pi by 8 table. This is same as the previous one as gate, but here we will be having pi by 4, which is 45 radians rotation will happen. Okay, so the representation is given as follows. Here we'll be having I pi e power I pi by 4 instead of I pi by 8, and here will be instead of I pi by 2. Previous one we had I pi by 2. Here we'll be having I pi by 4, and this can be written as 1 plus I by root 2. Okay, this is the only thing which you need to remember. It is also called as the pi by 8 gate, and it could be represented in the following form as well, in the exponential form. And the T gates circuit diagram is alpha 0 plus beta 1. If it passes to the T gate, we'll be obtaining alpha 0. 0 will remain same, but beta 1 will become e power I pi by 4 beta 1. And the truth table is also as follows. The truth table will be 0 will remain 0, 1 will become e I pi by 4 into 1, and this will remain same. Alpha 0 will remain same, beta 1 will become e I pi by 4 into beta 1. Okay, moving on to the multiple qubit gates. Here we have a single important concept, which is the controlled gates. Okay, what do you mean by controlled gates? So control gate is like a security card. Okay, for example, if A is true, then only B should happen. Like that kind of if condition is there, right? This is called as control gate. In this case, A is the control gate and B is the target gate. Okay, so if A is true, then only something will happen to B. It acts as a security to B. Okay, it checks if A is true or not, then only the operation will happen on B. This is called as multiple qubit gates. Here we'll be having a control gate as well. Okay, a few types are there. The first one is the controlled NOT gate or C NOT gate. What will happen here is, here we'll be having A and B here. If A is true, then only the change will happen in B. Otherwise, change will not happen in B. Okay, A is called as control qubit and B is called as a target qubit. Okay, so the equation is given as follows. Matrix representation also very simple. 1 1, and here you have to put 1 1, and rest all are 0. Okay, this is the design you have to remember. And transformation equation could be given as A B here, A comma B not A. Okay, B should change only if A is true. And then the operations on C naught for the 4 inputs 0 0 0 1 1 0 and 1 1. If we do the C naught operation on 0 0, what will happen is, so suppose consider 0 0 here, which is given as 1 and 3 zeros, and this is the NOT gate operation 1 1 and 1 1. When we multiply it, we'll be getting 1 0 0 0. That means, since 0 0 means what, so what do you mean by 0 0? 0 0 means this is A and this is B. If A is true, B should change, right? If A is true, B should change. Since A is not true, B will not change, so this will be 0 0 itself. A is not true, so B will be remaining same, which is 0 0. Similarly, we have 0 1. A is 0, B will not change, so since A is 0, it will remain same, 0 and 1. And for the 1 0, what will happen? Since A is 1, 1 means it's true, so B should change, so B will change here, B will become 1. And if it is 1 1, it will change to 1 0. Why? Because 1 is A is true means B should change, B will change from 1 to 0, and A will remain same, so it is 1 0. Okay, so the truth table will be for 0 0. Whenever A is 0, the input and the output will remain same. If A is 1, only the B will change here. The 0 is here, it will become 1, and 1 is here, it will become 0. Okay, next we have the swap gate. Swap, as its name suggests, it means it's swapping two qubits. Okay, it's swapping. So the matrix representation is as follows. 0 1 1 is here, like leaving one bit. Okay, not continuous, leaving one bit, 1 is here. Okay, and the operations will be very simple here. 0 0 swapping, again it will remain 0 0. 1 0 0 1 will become 1 0, and 1 0 will become 0 1, and 1 1 will become 1 1 will stay 1 1 only. This is the schematic representation of the swap gate, and this is the equivalent circuit symbol. Okay, and the truth table for the swap gates also very simple. 0 0 will remain 0 0, 1 1 will remain 1 1. This will turn to 0 1, and this will turn to 1 0 will turn to 0 1, and 0 1 will turn to 1 0. Sorry, this is 1 0. Okay, it will change. Next we have the control Z gate. What does control Z gate do? It has a control bit A, and such that if A is true, then it transforms B. Okay, it does not change B, it transforms B with respect to the Pauli's Z principle. Okay, so the matrix is as follows. Just put all 1 here except the last one, which is -1. The operations on CZ gate for the 4 inputs will be as follows. For 0 0, if we apply the CZ gate, what we will be getting is 0 0 itself. If you apply for the 0 1, we will be getting 0 1. For the 1 0 also we'll be getting 1 0. Just for the last one we'll be obtaining minus 1 1 here. Okay, very simple. 3 remains same, only the last one will change because we have in the last one minus 1. Okay, so the control Z gate and the truth table is as follows. Here we will be drawing this diagram for the schematic circuit, and this is the truth table. All are remaining same except the last one, which is just getting one minus here. Okay, so for CZ, which is control Z gate, we'll be obtaining minus 11 here, and rest all will remain same. Okay, and then moving on to the last gate, which is the Toffoli gate. It has three inputs. Okay, since till now how many inputs you consider? Two inputs, but here we have three inputs. Okay, so what are those three inputs? It is known as CC not gate. Okay, means controlled not gate. Okay, two are control input and one is the target input. Okay, observe carefully. We have two control input and one target input. Okay, so the target inputs change will depend on the two control inputs values. Okay, if both the control inputs is 1, then only change will happen. Okay, if both the control inputs is 1. Okay, the matrix is a huge matrix here. How many we have? 1 2 3 4 5 6 7 8. 1 2 3 4 5 6 7 8. Okay, just make an 8 by 8 matrix, and till the 6 places we have to put as 1 in the diagonal, and then the last one will change. Okay, 6 are same and the last 2 will change. Okay, that's how you make the matrix table. And after that, the truth table is as follows. See, the first two inputs are the control inputs. This is the target input. Okay, if these both are true, then only this should change. These both are true means it should be 1. So that happens only in the last two cases. In last two cases only these both are 1. So when these both are 1, just reverse this value. This will become 1. Just reverse this value. This will become 0. Rest all are same. They, above all the things are same. See, 101, 100, 011, 010, 001, 000. Okay, just have to remember the last two will change. That's only we have put in here last two as 0 1 and 1 0, and the rest will remain same, so it is 1 in the diagonal. Okay, and representation is as follows. If A and B both are true, then only the change should happen. Okay, so the previous one, you remember, it was just C, like it was B and means not A, but here we'll be having, since it depends on both A and B, here we'll be having C not AB. Okay, so this is all about the module 3 of the quantum computing. The numericals I'll be uploading in a separate video. And thank you so much for watching. Make sure to hit the like button, subscribe my channel for more videos like this, and I'll see you in the next one.